everyone, in this video we're going to be learning about linear equations. So we learned about linear equations or the format of them in the past, but let's define this to be a linear first order differential equation. And so it has the form a sub 1 times the first derivative of y with respect to x plus a sub 0 or a naught times y equals b. And so a sub 1, a naught, and b all only depend on the independent variable. Normally that's going to be x. So they're functions of x only. And so there's going to be two situations when this linear first order differential equation can be easily solved for. We can easily find a solution. And quick reminder, a solution to our differential equation is the original function whose derivatives are involved in this equation that satisfy this equation. And so number one situation would be if a naught is 0. So if you go back to your form for your linear equation here, if a naught is 0, this term is gone. And so you just have a sub 1 times the first derivative equals b. And then you can solve for y just by doing some quick division, divide by a sub 1, and integration. So the other situation where this can be easily solved is if a naught actually equals the derivative of a sub 1. So if this factor right here that depends only on x is the derivative of this factor right here, then we can easily find a solution. And so it's because it's the product rule from differentiation, kind of if we work it backwards. So look what we end up with. So I'll start from the back here and go to where we were just at so you can see it. So if I told you to take the derivative of a product, a sub 1 times y, you would use your product rule. You would say the derivative of the first term times the second plus the derivative of the second times the first. And so notice what we have. The derivative of a sub 1 is a naught, according to case 2 here, times y. And then the derivative of y is dy dx times a sub 1. And so we take this expanded version of our product rule and we go backwards with it, if you want to think of it like that. And so once we have that, we have the derivative of a product, and then we can just quickly integrate. So if we just integrate both sides of this equation, the integral undoes the derivative here. If you think about your fundamental theorem of calculus, the version 1 of it, you integrate the derivative. So just think of those as undoing each other. And so if you integrate b on the right side, you would then just have to divide out this a sub 1, and that's how you would get your function y, your solution. So both of these two situations, either when the term with involving just y is gone, it's 0, because a sub 0 is 0, or when a sub 0 is the derivative of a sub 1. This is more so number 2 here, the situation we're going to see more often. Okay, so case 2 can be achieved by multiplying the original equation by a well-chosen integrating factor, which we call mu of x. So case 2, what's going to happen is a lot of the time we're going to get to case 2 by creating it. So what we're going to be working through in this section is we're going to be finding what's called this integrating factor mu, so that when we multiply by that mu value, we end up getting this nice expanded product rule. We can go one more step here and write it as the derivative of a product and then get to the solution. So the method for solving linear equations, we're going to break it into some steps. Step 1, write the equation in standard form. And so in this case, we have dy dx plus p of x times y equals q of x. And just so you know, this is the same thing we had just a moment ago, just different notation. Okay, so same linear equation we have already had, but we're just letting p of x represent what happens when we divide a naught by a1. And then q of x is just b divided by this a sub 1. Okay, so just kind of cleaning up the notation, and we're calling this standard form. Then step 2 is to calculate the integrating factor mu of x. And so this is mu of x. So you want to remember this equation because this is how you're going to calculate this integrating factor. So mu of x always equals e to the power of the integral of p of x dx. So what you have to do is you have to find p of x from your equation, you have to integrate it, and then raise e to that power. Once you've done that, That's mu. That's the integrating factor. Okay, so just a little bit of information about this. Mu prime is mu times p, such that the integral of 1 over mu d mu is the integral of p of x and dx. Okay, so just so you know where mu comes from, it's going to end up satisfying our nice situation, case 2, where we can use the product rule. So just like we had said earlier, if case 2, a sub 0 was the derivative of a sub 1, it's sort of that same idea here. Mu p is the derivative of mu. Okay, so just some quick steps to show you why this works out. If you integrate both sides here, notice what you'd get. You'd get natural log of mu equals integral of p. And then if you raise both sides of this equation, you say e to the power of both sides of the equation. Then what we have, remember, e raised to the ln power undoes itself, and you're left with the argument of the natural log. So you're left with mu over here. And so that's where this comes from. So that's why we have mu equal to e to the integral of p dx for the exponent. Okay. Then our third step is once you find mu, your integrating factor, you're going to multiply by it. So you're going to take your equation in standard form here, and you're going to multiply both sides of the equation by mu. So it's going to look like this. Okay, so just multiply mu to both sides of the equation. And then notice what this is. By definition, mu times p is mu prime. So this is case 2. This is what we're creating. So notice what we have. We have mu times the derivative of y plus the derivative of mu times y. So that's just our product rule again. That's that whole case 2 thing that we're trying to achieve. And so what we can do is kind of work it backwards and say that this is the derivative of a product. If you want to double check, go forward here and say the derivative of this product, mu times y, and you say derivative of mu times y plus derivative of y times mu, just to double check. And once we have that nice setup here, we're going to go to our last step, step 4, integrate and solve for y. So if we integrate both sides, think of the integral as undoing the derivative here, and you're left with mu times y, and then you would just divide out the mu to the other side, and then we would get y. Okay? So that's going to be our process for solving these linear equations. We'll work out some examples so you see how the steps go, but you want to remember these 4 steps. So first example, find the general solution to this equation. Okay, so first let's try to write it in standard form. And so what I'm going to do is I'm going to multiply both sides of the equation by x so that we have the derivative by itself, or like with a coefficient of 1. So if we times both sides by x, we end up with the derivative of y with respect to x. Just quick with your rules of exponents here. 1x in the numerator, 2x is on bottom. So this is 2 over x now, a y. And then we get an x squared cosine x. Okay, so now this is standard form. And we want to match up what we have here with what our standard form looks like, because we need to identify p of x. Okay, so notice what p of x is. It's going to be this negative 2 over x. Okay, so we're going to use that to do step 2, which is to find our integrating factor, mu. So we found p of x, and then we integrate. So we're going to do this in steps. So you don't do it all at once. You can if you want, but we're going to integrate p. So integrate negative 2 over x, and that's going to give us negative 2 natural log of x. And then from your rules of logs, remember that can become the power. So that's ln of x to the negative 2. And then the next step for finding mu is to say e to that power. So then mu equals e to the ln of x to the negative 2 power. And remember, e to the ln power undoes itself, and we are left with the power. So mu, in this case, our integrating factor, is x to the negative 2. So we wrote our equation in standard form. We found the integrating factor. And now step 3 is to multiply by the integrating factor. So we had our standard form of our equation in the parentheses here. We're multiplying both sides by mu, by that integrating factor. Do a little bit of simplifying here. And then notice what we have. The whole point of introducing mu, finding it and multiplying by it, is to get right here and to this very next step. So that's the whole reason why you're timesing by mu. Once you've multiplied by mu, you should notice and double check that this is the result of the product rule. Okay? So this is the derivative of x to the negative 2 times y. Let's verify. You don't have to do this every time, but I want to make sure you understand. So if we go backwards here, derivative of x to the negative 2 is negative 2x to the negative 3 times y. Okay? Product rule. Plus x to the negative 2 times the derivative of y. Okay, so that's our product rule from calculus 1. So just verifying that this is equal to the derivative of this product. Once we have that, then we can move on to our last step and integrate both sides and solve for y. So we're integrating the derivative. Those are going to undo each other. And then integral of cosine is sine. And then one more step. We want y equals. So let's just divide by x to the negative 2. And we end up with y equals x squared sine of x plus c times x squared. And this is for x greater than 0 because that was given. And so we found our unknown function, which is the solution to our differential equation. Let's try another one. Find the value of y of 2 for the initial value problem. Y prime plus y equals square root 1 plus cosine squared of x. And then it's an initial value problem, so there's got to be given some more information. And so also we know that when you plug in 1 for y, or 1 into the function y, you get 4. Okay, so standard form, step 1, done. Just take a notice that we have our standard form, the derivative of y plus something times y. The something in this case is an invisible 1, equals a function of x only. Okay, so standard form is done. Recognizing that the coefficient on y is 1, that's our p of x. So starting to find mu, just integrate p of x, which is 1. So integrate that to get x, and then raise e to that power. So our integrating factor is e to the x. Moving on to our third step, multiply by that integrating factor. So we're going to multiply our equation, same equation up here that was already in standard form, by our integrating factor, e to the x. Okay, and then go ahead and expand that out. And then there's our product rule. Just double checking again real quick with you guys. Derivative of y times e to the x plus the derivative of e to the x, which is itself, times y. Okay, and so then we get to our fourth step, which is integration. Okay, so we integrate and solve. And on the left side, the integral undoes the derivative here. The right side is pretty ugly. And so if I just divide by e to the x, here's our implicit solution. Y equals 1 over e to the x times this integral. Okay, so if it just wanted an implicit solution, we could go ahead and stop here. Well, technically it's explicit because y is solved for. But the issue is we were asked for something very specific. So this one's a little different than our previous example. We need to know what y of 2 is. Okay, and so I can't just plug in 2 for x because I have to integrate this first before I can plug in 2. And so that's going to be the tricky part here. So this solution is not expressible in terms of elementary functions. So we're going to use a numerical algorithm called Simpson's rule to perform definite integration and solve for y of 2. So what I want you to notice is we've done our 4 steps. We found our solution here. But because we were given this initial value in this direction of finding a specific y value, we have to go further. So the whole process of solving our linear equation, it's done right here. And now we're going to get into some kind of trickiness with our math. I'm going to walk you through it, so don't worry. But I just want you to know that we're stopping kind of one part here and moving on to a new part to find this particular y value. Okay, so here's how this is going to work. We're going to integrate from our initial x value. So notice what we know here. When we plug in 1 into our function, we know the outcome. So that's our initial x value. X is 1. And we're wanting to know what happens when x is 2. That's the actual question. So that's where my limits of integration came from. So that's sort of just jumping right back to this step right here. So I just put limits on my integrals. So I'm making this now definite integration. Okay, so same step from right here, just with limits of integration. Okay, so let's go ahead and keep going. And so the left side, we're easily able to integrate that. We just integrated the derivative. We're going to evaluate from x is 1 to 2. And so notice what we have here. We plug in 2 for x, but then y is a function of x. And so we have y of 2. That's what this is saying. And then over here, plug in 1 for x, and then y of 1. So we have to find those values. We know one of them. We know that when you plug in 1 for x into the function y, you get 4. That was given. But what we don't know is what happens when you plug in 2 into the function y. That's the whole point of the problem. That's actually what we were asked to find. Okay, so what we're ending up trying to do here is we're going to try to solve for this y of 2. Okay, so if I do a little bit of algebra, I'm going to add this e times 4 to the other side and divide by e squared. That's how I got this quantity here. So now y of 2, I know what it equals. It equals this craziness here. And now the hard part is still this integral that we're going to focus on. So we're going to use Simpson's rule for that. Okay, so Simpson's rule, let me explain that to you real quick. So you don't have to worry too much about this, but let me just explain a little bit. If you want to solve a definite integral, and it's not very easily done, then we can use this rule, and it says that this definite integral is approximately equal to this calculation on the right side. And so delta x is b minus a, which is your limits of integration being subtracted, over some even number n. And then f of x sub 0, x sub 1, and so on, all these values. F is your function, your original integrand. Evaluated these different x values, and those are found from taking your starting point, and in this case a, and adding your delta x to it to get the next x value. Okay, so again, you don't have to worry about this too much. I just want to show you what it is, and we're just going to use it to approximate this solution. And so for us, we're going to go ahead and let n equal 2. That gives us a delta x value of 1/2. And so our integral, so notice what y of 2 is. It's this quantity here, but I'm just focusing on only this integral. So I'm going to add in this 1 over e squared later, and this plus 4 over e also later. So this integral is approximately equal to our delta x, 1/2 over 3, times f of 1, our starting value, plus 4 times f of 1 plus 1/2. That's where the 1.5 came from. And then we would keep going until we had our last term. We're stopping at 2. Okay, we're going from 1 to 2. So we're actually already right here in the formula. So plus f of 2. And so then we take these numbers, we're plugging them back into our function, which is our integrand. And so everywhere there's x, I put a 1 for the first f of 1. And then plus 4 times, everywhere there's an x, I put a 1.5. And then last one, everywhere there's an x, put a 2. Calculate that, and we get about 4.84. And so we know that the integral part of this computation is about 4.84. So just add in the other parts to it. We had 1 over e squared times that integral value plus 4 over e. So that's about 2.127. So finding the solution to our linear differential equation, that part was done a while ago, but because we were asked for the specific y value, that's why we had to do this whole process with Simpson's rule. So just for finding your solution, you follow our 4 steps that we worked through. So the last thing to mention to you guys is just about existence and uniqueness of a solution. So for the initial value problem, notice this is our linear standard form here of our equation, and it's an initial value problem, so it has some initial value given. If p and q are continuous on some interval that contains an x sub 0 or x naught value, then there exists a unique solution, and it's of this form. Okay, so that's our theorem. If you remember, we've actually seen an existence and uniqueness theorem previously, and just so you know, the difference between this new version and our previous one is that the previous one had a more limited interval that the unique solution existed on. This one has a whole interval anywhere from A to B that this solution can be existing and unique. So just something to mention about that. All right, so that's it for this one. The process for finding your solution to your linear first order differential equation is just following those 4 steps. All right, take care.